Hello and welcome everybody to my protection course in electrical power systems. Today we would like to talk about distance protection, and we specialized in the distance protection basics and in the machinery, so the distance protection relay. So the job of distance protection is, if we have a line in an electrical power system and there is a fault, we would like that this relay that is indicated with a red circle trips the fault, and that it does not trip the fault for a fault that is behind this. So how does the relay discriminate? There are two approaches. One is the classic approach. So the classic approach is that the impedance magnitude is measured, that the direction is determined, is it downstream, is it upstream, and that accordingly a time is respected when to trip. And this is versus the electronic circuits or microprocessor-based protection, which just determines in the impedance plane the complex impedance and decides whether it is inside or if it's outside the so-called tripping area. So I would like to start with the classic approach, and for this purpose I show you a voltage source impedance, the relay given as R, and a line on which we have at varying positions the fault. So if such a fault occurs, we have a fault current to this fault point, which is going through the current transformer, and the replica of this fault current is fed into the protection relay, into the right coil, which is the current coil. So at the current coil, we have a current flowing through this coil, and it magnetizing and tries to pull this lever down to its side. On the other hand, we have a voltage, a residual voltage, which magnetizes the restraint coil, the voltage coil, and these two forces act either to the right or to the left side. And if we have one point where they are equal, the trip force is strong and we activate a trip on this. Now, if we have a fault or a high impedance at the far end or behind this line, the restraint forces are higher than the trip forces, the current forces. If we move further in, one side comes down, which is the restraint force, the voltage source, because the closer we get to the relay, the less residual voltage is monitored there. And on the other hand, the current will go up. And that goes on till we at a certain point have an equilibrium, and behind this we have a trip zone. So this trip zone will mean that at the tripping point the ratio between voltage and current forces, or voltage and current, is at a critical value, and that is the so-called tripping impedance, Z star. And if the fault moves in further, then the residual voltage, the restraining force, gets even lower, and the currents will get up. So in this red area we have a trip area, and this is the tripping area, and by this means such a relay can discriminate between the trip zone and the restraint zone. The other approach for distance relays, in order to determine is the fault on the own line or is it beyond this, is the impedance plane approach. So we start again with the same fault impedance model. We have a source, we have the relay, and we have a line on which there may be a fault. This line can be represented by the pi equivalent circuit, which consists of a resistance, an inductance, and two capacitances, which usually are assigned to the left and to the right side. Now, if we have a fault, this equivalent circuit is short circuit, and that means that the downstream capacitance is short circuit, so it does not play any role anymore, and also the upstream capacitance can be usually neglected because the capacitive fault current is so small compared to the high short circuit current that it is neglected. So the capacitances are left out, and we have this fault circuit of the first order, we call it. Now, in the impedance plane, this is represented by 2 points. The blue is the resistance and the black is the reactance, and together they add up to the impedance. Now, if the fault point moves forth and back from this position, then also the R and X vary, but they vary in the same ratio, and that means that this fault point moves along the so-called impedance line. And there is always a limit where we say if the fault is before this characteristic tripping point, we will trip. If the fault is behind it, we will restrain and wait. So in the relays, there are 3 conditions to be fulfilled. The most important one is the X that is measured by the distance relay, is it below this characteristic value? Because X is proportional to the distance from the relay to the fault point. The next condition is the resistive part lying in an appropriate phase, angle and appropriate place in this impedance plane? And the third condition is the whole impedance lying in the first quadrant? That means that it is forward, that it is downstream and not in the reverse direction, which would mean restraining. Now, if these 3 conditions are fulfilled, we have a trip. So this was today's lecture about distance protection basis, and I thank you very much.